Little's law. If you consider average values of the three measures of process performance that we defined, the inventory, flow rate, and flow time, we will see that these three measures are connected. They are connected by the formula which is commonly known as Little's law. So for short, this formula we can write it as inventory I equals flow rate times flow time. Remember, this only works when the IR and TR averages. And it's very easy to actually kind of know this formula without memorizing it. When you observe the units of the measures on both sides have to agree. So if inventory, for example, is people, right? If this is the service, so the unit here is people for I. For R, the unit will be people per flow, per unit of time, for example, per hour, right? And the unit of time will be just hours, right? So you'll see if you multiply people per hour times hours, the hours can be simplified, and then the units on the left and the right-hand side agree. This is a very interesting law because it allows us to find one of the measures when we know the other two measures. And also it has important implications because often we are interested in increasing or decreasing one of the measures, and we can affect it indirectly by holding one measure constant and changing another. For example, if we hold throughput or flow rate constant, and if we reduce inventory, we will at the same time be reducing the flow time, right? If you reduce inventory and the flow rate is constant, then of course flow time must be reduced as well. And remember, these are all on average values. If, for example, we hold inventory constant and we reduce the flow time, then the flow rate must be increasing because if they are multiplied and the product must be constant, reducing this must increase this, right? This law was first discovered by Professor John Little from MIT. So here are some examples of applying this law. So suppose a fast food restaurant has enough space to sit 25 customers at the same time. And suppose that the customer spends on average 10 minutes in the restaurant. How many customers can the restaurant serve at most during a rush hour? So to solve this problem, we need to observe that 25 customers will be inventory if the restaurant is full, right? So we know I will be 25. So in this first example, I equals 25 customers, right? And what else do we know is if we know the average, and so notice, by the way, maximum number, in this case, we will consider it equivalent to an average number, right? And then 10 minutes will be the flow time. It will be 10 minutes. This is exactly as given. Average time customer spends is 10 minutes, right? We can convert it to hours. So it's 1/6 hours, 1/6 of an hour, right? So from Little's law, we know that, right? We know in the Little's law, I equals R times T, right? And now we're interested in R, so we can solve it as R equals I over T, right? So that's the solution that you see here. R equals I over T, 25 customers divided by 1/6 hour, right? Will mean we actually 25 times 6 customers per hour. So that's how many customers can serve per hour, right? We could have calculated it per minute as well. Another example, suppose the same restaurant could reduce the average time spent by a customer during rush hour to 7.5 minutes, right? Why would the restaurant want this? Well, because if it's still full, if it still will have on average 25 customers present in the restaurant, but each customer will spend less time, as we said, this should increase the flow rate, right? If you decrease the flow time, keeping I constant, then that must mean the flow rate is going to increase. And the flow rate is a very important measure because it is the basis for revenue for the fast food restaurant in this case. So if you reduce this, right, then T becomes 7.5 minutes. I inventory is still 25 customers. 7.5 minutes is 1/8 of an hour. And so if you do the calculation, you'll find out now the flow rate has increased from 150 customers per hour before to 200 customers per hour now. And as I said, this could be a very desirable improvement in a fast food restaurant, because if every customer leaves some money in the restaurant, buys on average a meal, let's say equivalent for of $10 spending, then 150 customers per hour means 150 times $10, so $1,500 that of revenue per hour, whereas 200 means $2,000 of revenue per hour. And you'll see this might be something that the fast food restaurant might be interested in doing.